So let's see. So I'll introduce myself a little bit. I'll run through kind of a brief overview of SpaceX just to put everyone on the same page, and then I want to talk a little bit about how we write the flight software and how we do test and validation, and a little bit of kind of how my history intersects with the way SpaceX is developing software. So to start, I joined SpaceX about 2.5 years ago as their software vice president. Before that, I was at Google for 10 years, and most of that time I was in site reliability engineering. I started at Google originally as part of the production team, production on-call, and ended up becoming the manager of what was the on-call of last resort for Google for most of that time there. So that was the team with kind of the primary or ultimate responsibility to be able to dig in and diagnose from first principles any problem that would come up across infrastructures. So that allowed me and my organization to be able to claim correctly that we had root on every system at Google during the period that we were in that we held that responsibility. So after 10 years at Google, 2.5 years ago, I joined SpaceX. They called me and I said, I can't imagine I'm your guy. And we got to talking, and it turned out there was a pretty good fit there. So from here, I'm going to go and just kind of give you a brief overview of what SpaceX has been up to, and then we'll dig into software development and validation. So some of the core things here, SpaceX is actually a pretty old company, right? It's been around for 14 years. The early years were extremely austere, working on Falcon 1 and worked through a number of failures there. But the core mission is to revolutionize space technology with the ultimate goal of building the foundation to allow people to live on other planets. The core tenets are reliability, speed, and reusability. So let's see. So let me give you a quick overview. Hopefully this video plays normally. Volume up. All right. So a quick overview of SpaceX.
DC confirms flight computers in startup.
Second stage pressing.
Tanks are at flight pressure.
F9 switching to internal power. T-minus 5, 4, 3, 2, 1, 0. Liftoff of the Falcon 9. Falcon 9 is clear the tower.
First stage propulsion is nominal.
Here's a look at the Dragon capsule making its way towards the International Space Station.
Station on 2, we see Dragon at 20 meters.
And capture is confirmed.
4, 3, 2, 1, launch.
All right. So SpaceX has a number of operations going on. Right now we've got satellite work going on in Seattle. Our main factory is in Hawthorne, and that's where most of software engineering and other engineering occurs. We've got launch sites at Vandenberg and the Cape, and then we have our test facility in McGregor. So we're working on a launch site that we're building out in South Texas, which some of you know about, and then we have an office in DC as well. So let's talk about our vehicles. So Falcon 9 is a 9-engine boost stage, recoverable. We have successfully landed the first stage. Falcon Heavy is currently in development, looking to fly it sometime next year. It's made up of 3 Falcon 9 first stage boosters, resulting in 27 engines, and then 1 second stage. And then we've got basically 2 variants of Dragon right now. The first one is Dragon 1, which does cargo missions to the International Space Station. And then Dragon 2, which is coming later, will be its first missions will be for crewed flight to deliver crews to the ISS. We'll also use that platform for cargo missions as well in the future. Let's see. So Falcon 9, 9 Merlin engines. You've got the first stage. It's basically a series of tanks, right? So you've got the 9 engines on in the thrust section. And that's what we call the octaweb. And then you've got the fuel tank, liquid oxygen tank separated by a common dome. And then there's a dome at the top that is the oxygen, that is what we call the ox dome. Then you've got this inner stage where you've got the grid fins sticking out of. And then the nozzle of the second stage is nestled down in the inner stage. And then the second stage begins. In this photo, we've got Dragon on top of the second stage. And the second stage made up, again, of a fuel and oxidizer tank and 1 main engine. So let's keep going. So because I want to get into kind of software development quickly. The ongoing work that we're doing right now is around commercial crew, reusability, and the Mars program. So Elon announced the Mars program earlier this year, and you can go online and see some of those videos. Reusability is near and dear to our heart. It is the foundation for our continued success, and the idea of throwing away all of this hardware on every launch seems kind of nuts. So, and there's no way we're going to get to Mars doing that. So we've spent, the time that I've been at SpaceX in the last 2.5 years, we spent a lot of effort on doing reliable first stage recovery, and now we are looking into next year to actually fly our first reused rocket. And then commercial crew is a parallel effort right now to restore domestic capability for crewed flight to low Earth orbits. All right, so let's talk about software engineering at SpaceX. So the mantra is reliable, fast, and reusable. It is both the company's mantra and is also what we try to do in software as well. We kind of build our development methodologies around achieving vehicle objectives. So successful landing of the first stage could be considered one vehicle objective. And then a bunch of the design and engineering falls out of that. We do in-house development of all flight software for all SpaceX vehicles, Falcon 9, Falcon Heavy, our 2 Dragon variants, and also satellites. All of that is based around a common code base. There's a lot of specialization, but we try to keep it within one code base for reuse specifically. Ground launch mission and now flight display software are also developed in parallel to flight software in-house by separate teams. And then we have a simulation team that builds all of our physics and vehicle and phenomena simulators. And they work in concert with guidance, navigation, control, and flight software. It's kind of, they serve both sides of that, and I'll talk about that a little bit later. Then we have a software test team, which is their primary responsibility is verification and validation in-house of our flight software. We occasionally do independent verification where we'll bring someone from the outside in, but every feature we design, every change we make needs to be validated by our software test team. And then we have an automation team, which is focused on, one of the things that I'll talk about some of their great work has been our continuous integration system that they've built. But they are also responsible for data storage, telemetry, automated analysis, and a number of other internal systems. So let's take a step way back and talk about computers, because I like to kind of start this talk. If you look at computers in aerospace, computers in this industry, computers used to be people. They used to be brilliant mathematicians who were also very accurate and very fast. They tended to be women over time. The men would use that role as a stepping stone, but it was kind of a terminal career for women. But throughout, it started. You could see it from the moment that people were started to be able to break up math problems, that they started to build these groups of computers. And you saw that strongly in astronomy early on, and then later in aerospace. So this is Katherine Johnson. She was part of the West Area Computers at Langley. And West Area Computers was this segregated group of brilliant black female mathematicians. There were other groups of computers at Langley and in NACA and NASA, but this group was, Katherine Johnson is of particular note because she was very well known for her speed and her accuracy, so much so that John Glenn demanded that she be the one to calculate his orbit on Mercury Atlas 6, his first orbital flight. She also went on to be the person who calculated Apollo orbits, and this was actually critical because Apollo was this transition to digital electronics, and her hand calculations were then used to, in some ways, qualify the outputs of the digital electronics. And so and I'll use the word equivalency a lot in this talk, by creating that equivalency, that allowed them to build confidence in this new digital era of computation. She had a long 40-year career at NASA and did some amazing things. And there's a movie coming out about her in January that I really encourage you. Well, her and two of her colleagues, Dorothy Vaughan and Mary Jackson. And I encourage you all to see it when it comes out. So now we get back to software engineering. So again, this transition from hand calculations to digital electronics and digital computers brought in this new field of software engineering. And previously, it had never been considered engineering. It was software development. It was generally considered kind of a dark art that people in the back room did. So Margaret Hamilton was the director of the software program for the Apollo guidance computer, and she has been kind of credited with bringing software engineering, the term software engineering, into the forefront. She didn't necessarily invent it, but she used it a lot. And her reason for doing this was because she both wanted and needed the art of producing software to be treated with the same level of respect and the same level of care and the same integrated design model as hardware, electrical, and structural engineering. And then obviously, her peers found it kind of amusing to call software development engineering. Now, both of these women received a Presidential Medal of Freedom. Margaret Hamilton just a few weeks ago, and Katherine Johnson last year. So it is nice to see people finally being recognized for their contributions back then. So actually, I should say, getting back to the production of software and treating it as an engineering discipline and treating it with care. One of the things that came out of that, Margaret Hamilton spent the rest of her career focused on producing reliable, robust software, and has built a career around it. Had her own company and consultancy for a while. Separate to that, as the rest of the industry, and specifically the Defense Department, started dealing with software more and more, they produced standards like DO 178B and C, which are the aerospace software development standard. The development and test process for DO 178B is on the left. And kind of the classic diagram for waterfall development is on the right, and you'll notice there is an awful lot of similarity. Also because waterfall development did become much more formalized from the Defense Department as they started having more and more software projects and being able to contract out for software projects. This became a very big deal. One of the challenges with DO-178B and waterfall development in general is it's very front-loaded on requirements and design, and DO-178B and C to the point that there's almost this belief that if you get planning requirements and design correct, the coding, the actual implementation, is not the most important part. It's not the hardest part, and it's not the part to apply your most skilled engineers. It comes to, if you do planning requirements and design correctly, you don't need to necessarily worry about how the code is being developed, because the traceability in the whole process will catch any deviation. SpaceX chose not to use DO-178B and C as their primary development standard, and has an own internal software development standard that we have produced and demonstrated equivalency with DO-178B. But we kind of have gone our own way a little bit there. There are places where we still have to treat this process with a tremendous amount of respect and demonstrate true traceability back to this standard, because it has served the aerospace industry very well for a very long time. The challenge at SpaceX is we often have no idea what we are going to do when we embark on doing it. We have a vehicle objective like landing and recovering a first stage, but how we're going to get there is fairly unknown. And so we need to be able to do implementation. I mean, this is going to sound awfully agile. We need to get to implementation and iteration much faster, and then be able to back out planning and requirements later. So, innovation, reliability, and upfront cost. We've got waterfall development, which when done by these standards is very, very front-loaded, very, very heavy at the front end. So you tend to put a lot of time and energy and overscope a problem, because it has to be in the design, in the requirements to begin with, if it's going to be in the final solution. Getting back around is so expensive that you overload at the front end. Test-driven development, so waterfall development has this huge front-loaded cost. Test-driven development also has a huge front-loaded cost. I mean, almost all the development I've ever been involved in is test-driven. I'm not I don't want anyone to misunderstand me and think that I don't think it's worth it, but it is. I would say it's about a 30% overhead to do test-driven development as opposed to just implementing and doing tests later. There are times where that overhead is not appropriate, because that code is not going to end up being productionized. It's always a hard call to make, because when you have a working solution, there is always a very strong desire to use that solution in production. But there are times where you really just want to move quickly and produce a lot of speculative design and implementation to prove behavior, and you got to know when test-driven development is not appropriate for that. So getting back to agile methodologies and kind of getting back to this virtual cycle of development, test, iteration. Peer review is kind of buried in that model very tightly for producing safe software. And there are times, again, much like test-driven development, where you won't do that. But if you don't do test-driven development and you don't do peer review, you have to be really sure that software doesn't make it into the real world. Like you just can't rely on it. But it's a great way for moving quickly, and especially if you have a framework that allows you to do quick iterative test, it's great for experimentation. And experimentation and allowing for experimentation is kind of key to driving innovation rapidly. So there's this model that sometimes I describe as molding and casting. that we end up seeing crop up as a pattern a lot, where so guidance, navigation, and control will write an implementation of a flight control algorithm in C++. They won't do test-driven development. They will often not do test-driven development. They often will not do peer review, but they will have a C++ control algorithm that they can test, and they can test against our simulation software that they can use to demonstrate that that algorithm is sound and correct. And so that becomes like the negative mold. And then we use simulation to actually be the mold, where simulation, we have the outputs of simulation of how the vehicle behaves running that algorithm, and those outputs that result becomes the truth side of our simulation. And then that is used to produce an implementation guide from guidance, navigation, control that flight software then uses to produce a final flight software implementation. And then once the flight software implementation is produced, then it is run against the simulation as well and the truth side, and that is the cast version, and that is what we fly with. So at SpaceX, we also tend to, you can't just kind of come up with your own standards without spending a lot of time and energy on them. So we have leveraged coding standards like MISRA, which is the Motor Industry Safety and Reliability Association. So they have a C++ standard that is actually pretty good and pretty sane. And then high integrity C++ is also something we've been looking at quite a bit. So those two standards are very, very useful for developing C++ software in embedded high reliability environments. So let's talk about the triple string architecture. If anyone was here for the previous talk, you'll see some applications of some of the things that were discussed there. So we fly in fairly hostile environments. Like one of the primary concerns in orbit is radiation. So you're constantly trying to defend yourself from radiation, and SpaceX does not fly radiation-hardened avionics. They fly radiation-tolerant avionics, and the difference is our components can take a radiation hit, so our flight computers can take a radiation hit and may reset, but as opposed to a radiation-hardened system that should be able to take a radiation hit without impact to its function. So we have flight computers that we do expect the possibility of them of halting or resetting in flight. But what radiation tolerance allows us is the hardware won't latch up. The radiation hit won't cause the silicon to latch up and short out, and so we can reboot it and bring it back up. So we see this on Dragon on station. We see a couple radiation hits during a mission, and we'll have to kind of resync flight computers and bring them back up. But the way we manage these vulnerabilities is with the triple string architecture. So we basically have 3 redundant flight strings, and each flight string is made up of a flight computer and associated supporting hardware, sensors, telemetry systems, data acquisition, and output systems to the actuators. The actuators themselves, like engine controllers, have what we call a hardware median, where each string will be sending down a command, and the hardware median will basically vote and take the majority. So if on a good day, A, B, and C flight strings are sending like command 7, like maybe that's 70% throttle, or that's probably not. Anyway, because we don't throttle that low. Anyway, they're sending command 7 down to the hardware median. The hardware median passes 7 along. If we have what's called a desync, which is often if I don't know that we've seen it in flight, but a desync can happen because each string is running the same calculations, the same software, and they're not like completely tightly synchronized. So it's possible if for one flight computer to take too long on a control cycle and possibly skip a cycle. So if that's the case, it will be it will be looking at the same inputs, time offset, and may arrive at a different output because of that. And so that's one possibility of where we'd have a different output. And so if C string were to desync and send 5 down, we're 1 fault down, but we still get 7 through. 7 is still the majority on the hardware median, and we pass 7 on to the actuator. This gets more complicated when you need to build systems that are 2 fault tolerant. So in those systems, we have kind of a smart voting system that will, if the B string were to go out, so C is desynced, if B string were to lose power, the smart voting logic would accept the A string over the C string because the A string was the last consensus-driven result. So that allows us to lose both C and B and continue to fly. But whereas with the hardware median, it wouldn't be able to form a majority vote. So let's talk about Linux in flight. So the flight computers that SpaceX uses run Linux. They have for quite some time. The flight control process runs in user space. It is a C++ application that we compile in, and there are multiple Linux computers on board. So each string has 3. So you have 3 strings. So you have 3 flight computers. We also have Linux running on systems like the small system that manages telemetry and RF communications. So if you look towards like Falcon 9, you've got 3 Linux flight computers on every first stage, 3 on the second stage, and then you've also got 3 telemetry RIOs on each stage as well. So you end up with, basically a small cluster of Linux computers in flight that you are managing. We have shared code base across all of our vehicles, so Dragon, Falcon, and satellites, and so some ground support systems like our proxies that communicate with the vehicle are also running out of that code base. And again, that's all C++. So software testing and validation. The core of what we're able to accomplish for our validation model is what we call hardware out of the loop testing. So we actually take the flight software code base and cross-compile it to x86, and we run the flight processes in Linux containers. And so we can arrange the containers to be extremely flight-like. So we have a container for each flight computer, a container for other ancillary systems, and since we use Ethernet as the primary bus on our flight vehicles, we can use Open vSwitch to build a analogous fabric connecting the network together the way it is on the vehicle. So then our simulation side that is feeding inputs into the flight software runs alongside these containers and is basically hijacking the point at which data gets ingested from the data acquisition systems, from the sensors. And then the simulation side also accepts the inputs, so like engine commands, various valve commands, and simulate and creates this overall simulation of what the vehicle will be doing in flight. And then we have a separate, our software test organization has built this test orchestration system that manages each test and it can inject faults in a flight. So we can effectively, in software on your own desktop, on a developer's desktop workstation, run all of the flight software end-to-end in a full flight. So we can go from launch to orbit or launch to dock, in the case of Dragon, on a desktop and get very good exercise of the real code base. And so we can do that a lot. So this started as a way to kind of speed developers. It's also the environment that guidance navigation control uses to do a lot of experimentation in for changing things and seeing what ifs. And it's tremendously open up the velocity of development and innovation in our system. So then we step into kind of the next level of correctness, and we do hardware in the loop testing. And so some people call this HIL as opposed to SIL. And hardware in the loop testing is we have basically all the vehicle avionics laid out on a table or a rack. And it's the same simulation software, whereas it was injecting inputs and accepting outputs from the software directly in the Linux container environment. Here, it's actually wired to the inputs and outputs and driving analog signals directly to the sensors and accepting analog signals from the outputs. So it again simulates the entire vehicle function, and we also use the same test orchestration system to inject faults. And so we go from a software in the loop to a hardware in the loop test, and then we see things like process timings, process load, like do we have memory bus contention, do we have a network contention, things like that in real world. And so we can get a high level of, again, equivalency between our hardware out of the loop and hardware in the loop testing. And then as a final test, we will run the same test on the flight vehicle before flight. It's kind of an end-to-end equivalency all the way back to hardware out of the loop on our expectations of our entire test bed. But this is 5 minutes, okay. So this is kind of our end-to-end system. I'm going to speed up a little bit. Right. So continuous integration and test. So because we're using Linux containers, it's streamlined software testing. We've now been able to kind of customize our CI system to deploy this container arrangement and network and virtual network arrangement, so that every change as part of CI gets a full end-to-end HOODL. And then we also have our same continuous integration system doing running nightly HIDLs on our hardware test bed. So this is really kind of opened up our development cycle, because anyone who's ever gone from no continuous integration to having continuous integration knows it vastly speeds things up. Like test development, the kind of stability of trunk of your code base goes up dramatically, and the amount of time you spend debugging problems in other people's code, the amount of time you are spending testing your own code goes down dramatically. So the last thing I want to kind of touch on before, because I wanted to leave a little time for Q&A, hopefully we can do that. So I was a site reliability engineer. I started my career as not I studied computer science, but I was much more of a system administrator. Like in high school, I was doing Novell NetWare installs. Just out of college, although you'll never find it on my resume, I had my MCSE. And I got, I was working doing kind of software and sysadmin work on Wall Street, and then I got hired by Google. I got hired by Google as a software engineer in site reliability, and spent, but I transitioned from kind of being a sysadmin or a systems engineer to becoming a software engineering manager through that experience, and it really kind of helped me understand the process of producing reliable software and what that takes, and how much how much individual effort it takes, and how to build a group around that. So just quickly, I talk about my 3 A's a lot, which is authority, autonomy, and accountability. These are kind of the things I'm always trying to optimize for myself and for my groups and for an organization. Being in a role of responsibility like site reliability or DevOps, you end up automatically having a tremendous amount of accountability, right? When things fail, it's your fault. It doesn't it's probably not your fault, but people are coming to you for the answers and for remediation. So trying to leverage that accountability to then to gain some authority. So if I'm going to be accountable for this problem, I want the authority. I need the authority to be able to change the outcome. And so that's one of the things that we were successful at Google in doing. And what I saw immediately when I came to SpaceX was this culture of accountability leading to authority, and then authority gives you autonomy. And for a lot of people, that autonomy is very vital to innovation, not being micromanaged and being able to kind of take risk. So the kind of the core difference between site reliability and SpaceX has this culture of the responsible engineer. You can be the responsible engineer for a subsystem. You can, like we have for every flight, we have a flight software RE for that flight. And you end up guiding whatever component or piece you own end to end. You are ultimately responsible for it, and that culture, that ownership is vital. Like if you think you believe that something is a true risk to flight, you are obligated to stand up. You are responsible for that flight, and that I saw a lot of analogs coming out of site reliability. Like the buck stopped with me. We built an esprit de corps around, or a bunker mentality, if you want, around being the people who stood on a wall and defended the infrastructure from change sometimes. But getting back to trying to create an innovative environment, the only way you can have an innovative environment and maintain reliability is by driving this responsibility down to everyone who is capable of making change or capable of introducing instability into a system. And so seeing that transition to the company having this high responsibility culture and that being what drives the velocity with reliability was pretty eye-opening to me. But I think there are a lot of parallels in everything that we do that comes down to that. And then one of the last pieces that I want to just bring up is the culture of engineering and making sure that we always, with having authority on some level, being sure that we always treat ourselves as engineers, and the rest of the organizations that we deal with are treating us as engineers, because it's ultimately an integrated engineering problem that we're dealing with, especially when you have multiple disciplines, and making sure, so when I come back to Margaret Hamilton, like being treated like a real engineering function as opposed to being treated like a service function is a problem that everyone has, every group has, every engineering group has, and trying to step beyond that and taking the accountability that we have and turning that into autonomy is kind of the core challenge of producing fast, innovative systems. So that's kind of all I got, but I was hoping I'd have a little bit of time, I probably don't, to take questions. I can probably take one or two, and I'll stick around if anyone.
This is the last session, so we have time for a question. Please go to the mic and ask it, and if you feel like you need to leave, go ahead, but we do have time as long.
Yeah, I'll stick around for a little bit.
Who's your government regulatory body? And specifically, is it the FAA? And will the FAA learn from what you're going ahead and showing them? I mean, because innovation and the FAA don't go hand in hand.
We deal with numerous regulatory bodies in the government. The FAA is one, NASA, Air Force. It definitely goes both ways, right? We're very frequently trying to demonstrate that there can be a credible alternate path. At the same time, there are lots of standards and ideas that come out of our government partners that make sense. So frequently, we're always balancing, we will happily do the work when it makes sense, and we will at least try to push back and suggest alternate paths for things that don't look like they're the most efficient way to solve a problem.
Good luck. Thank you.
So some of us say that our project blew up today, and we're being silly.
Yes.
But your projects can actually blow up. And
Yes.
when you start putting people on your spacecraft, and you're putting all this pressure on your responsible engineers, what do you do to armor plate them as a person? when you experience failure?
Okay, so there's kind of two questions. So one, you kind of, a lot of people have talked about the kind of culture of a blameless postmortem, right? And I used to joke that when I wasn't dealing with spacecraft, when there would be failures, I would say find all the swords and jump on them, right? Like you should anything that you did, anything that you might have done to contribute to this, anything that you didn't do to contribute to this, air it now in a way that has no repercussions. So trying to make sure, like Google's talked about it a lot, and I've always believed very strongly in creating an environment of psychological safety, and how vital that is to innovation. And so that's part of it, is being able to be wrong, to look dumb, to fail, but dealing with failure in a responsible way so that you learn everything you can from it. Like failure is extremely expensive. It's one of the most expensive things that can happen, and so you really got to squeeze every bit of value out of it when it does happen. In terms of as we go into human space flight, that's kind of a whole different ballgame, right? It is very different. The responsibility goes up greatly. We can rely on the kind of the emergency escape systems, but it's still not a good day. So a lot, like we kind of up the level of validation and care and design that goes into those systems. But getting back to, at its core, it's being able to fail but with low repercussion on an individual level, right? Yeah.
Thank you.
Yep.
Hi. First, thanks. Very interesting talk. I'm Tom Lumicelli from Stack Overflow. I was wondering, so when you go to Mars, eventually the ship is going to have to be much more self-sufficient, because communication to mission control means you're really going to need to have mission control in a box that is on the ship.
Yes.
I was wondering, what are your plans around that, and are you eventually going to have software development out there, or are you thinking about that kind of on board?
So I normally cover this. So like Falcon 9 is completely autonomous from the moment the launch mount releases until for first stage until it lands again. The only command you can actually send to Falcon 9 in flight is the termination command to blow up if it's off course. And even that we're trying to we're working on a system that is an autonomous flight safety system that will manage terminate on board. So we do have a lot of experience with fully autonomous systems. The Mars platform will obviously have to be fully autonomous as well. Sending things into beyond Earth orbit on a software engineering side, there's a long history of shipping the hardware and writing the software later, and I don't imagine the Mars program will be any different. That we will be shipping updates from Earth to platforms. Sometimes shipping systems that are not yet functional, knowing that we'll have that transit time to finish the software.
Great. Well, Dell and HP seem to do that all the time. So so good luck.
Yeah.
Thank you.
Thanks. All right, I'll stick around down here, but if anyone wants to come up, you're free to. And thank you very much.